Alright folks, we're going to give this try number 2. So this is your somewhat crabby professor who basically just had a video delete itself, and now we're going to have to give this another try. So it's pretty short and sweet, so it could be worse, I guess. We talked at the end of class on Monday about air mets. Here we go again with the criteria that will be the basis for the issuance of an air met, so moderate icing and turbulence, and then things related to strong surface winds, low ceilings that are extensive, as well as obscuration of mountain peaks. And so we ended with this slide, the idea of how these look in terms of appearance. You see a small one here highlighted along the coast, at least relatively small, here for IFR and mountain obscurations in California. Mountains obscured by clouds and mist, conditions continuing beyond 21Z through 3Z. But then you can see other air mets that are very extensive here from the Dakotas through the Midwest out towards southeast Michigan. So they can encompass, you could make an argument that this is a fifth of the lower 48 that's encompassed by this air met right here. If we look at a written version of air met Tango, here we see for turbulence again, this is the WA bulletin. We talked about that in class the other day. Air met Tango, you have updates that basically are revising. Think of it as amending the air met in some ways. And so here we got a number of coordinates, not all that dissimilar from what you would see in a convective outlook. And then the meat of it, moderate turbulence between 22,000 and 40,000 foot flight levels. Conditions continuing beyond 21Z through 3Z, so they will give a tease for how things are expected to be maintained or evolve. Low-level wind shear potential within a subset of the aforementioned region. Here we got the Dakotas again through Michigan and Lake Huron, and so this is not going to contain all of that here for the low-level wind shear. A lot of information. Most folks are going to dig into this if it's of specific importance to them. Otherwise, the graphics usually do the trick. And so we can see here in Air met Zulu, looking at certain portions, moderate icing between freezing level and flight level 18,000. Gives some information about the freezing level here between 6,000 and 10,000 across various portions of the area. Again, one of the big takeaways here is the size of your air mets. Relatively large, encompassing multiple flight levels in most instances. It doesn't mean that the entire layer is turbulent, but instead of overcomplicating the process, like here, we could put out multiple freezing levels, maybe 6,000 to 8,000, 8,000 to 10,000. Here we can see even freezing level in other portions ranging from the surface, and that's going to be related to terrain and other things. So it would get overcomplicated, and so they'll make larger areas and then just make some specific details about what's going on within the air met itself. Looking at SIGMETs, SIGMETs are going to oftentimes also cover large areas, but not nearly as large as the air mets. And if you think about it, you probably have a large area with, say, moderate icing, but only a small component of that is going to have severe threats. And so we're going to really drill down pretty notably to get from our air mets down to our SIGMETs. And so we can get these for severe icing, severe turbulence, and widespread dust storms, sandstorms, and volcanic ash. Not common. That's one thing I would say about SIGMETs. These are not going to be something that you would go out every day and see at least a few SIGMETs. As we get into convective SIGMETs here on an upcoming slide, they are more common than other SIGMETs. Note, though, again, these are going to be related to conditions occurring outside of convection. Widespread dust storms within the United States, not particularly common. This isn't going to be a small-scale haboob or something blowing ahead of a convective line. But the volcanic ash SIGMETs are probably the most common of that final bullet. Think of things, for instance, across Alaska with some of the volcanic activity off the coast of Russia. And you can occasionally get some of these volcanoes that spew enough ash to where they can advect downstream a ways, and that's when we can get some of these volcanic ash SIGMETs. And so this is a single bullet slide again. Remember, this is 2.xx light. Also, the fact that this is important. So to continue my theme throughout the semester, we'll make Aaron our meteorologist today. And Aaron has put out an air met for turbulence, and he starts getting reports from Morgan, and a report from Emily, and a report from Brennan, and a report from Ryan. And based upon their experience, types of planes, he realizes there's definitely a threat of severe turbulence, at least across a portion of his AirMet area. And that is what is oftentimes going to be the catalyst for a SIGMET. Something that's going to trigger the meteorologist to realize that the threat may be a little worse than they were thinking or the models were outputting. But what we see here is the feedback going both ways. Obviously, the meteorologist is critical to be able to get a good product to the pilot, keep them safe. But conversely, we also need to be able to have the pilot feedback to the meteorologist to improve the products as well. And so it is a two-way street. It's generally a symbiotic relationship, and it's something that works quite well given both parties' vested interest in making the best product available. SIGMET here in size. This should look relatively familiar from a couple of days past. A little icing SIGMET here over the Omaha, Shenandoah, St. Joe's, Concordia, Kansas Metroplex. Relatively small in size, but still not to where we're looking at a polygon size for a warning per se. These are going to be decently sized, and it's not going to be designed to capture every specific severe event in terms of turbulence and or icing. And so we conclude the semester, with convective SIGMETs. Convective SIGMETs, detailed, specific forecasts for phenomena related to thunderstorms. And so remember, thunderstorms are going to be accompanied by severe or even worse turbulence, severe icing, low-level wind shear. And so as we've brought up throughout the semester, we're not going to issue products explicitly for turbulence when it's only being driven by thunderstorms. But we're also going to understand that thunderstorms are capable of producing all of this type of phenomenon. And so in some ways are some of the most dangerous phenomena that are out there for aviation. But in most instances, they're relatively identifiable, and with current technology, usually aren't going to sneak up on anyone, especially with some of our terminal Doppler weather radar features and other ways of having coverage in high traffic regions. And so convective SIGMETs are going to get kicked out when either thunderstorms are already in progress or expected to occur in the near future. And so it's one of those things where it's a little bit more on the nowcasting side of things than a true outward forecast. We're not going to put out, say, a watch 3 hours before the thunderstorms develop. We're going to really trigger a convective SIGMET when it is imminent or in progress already. And so we're going to put them out for severe thunderstorms. This probably goes without saying that severe thunderstorms can be quite dangerous to pilots. The embedded thunderstorm, the one that I've brought up on occasion earlier, the area of low clouds, stratiform rain with some convective showers, and then maybe an embedded cell or two. So you're sitting around, it's just kind of raining, and then all of a sudden you start to hear some rumbles of thunder. And that means that somewhere in this environment we got some more notable updrafts and downdrafts causing this charge separation. And this can be notably dangerous to a pilot. You're flying through an area of rain, and then all of a sudden you encounter a thunderstorm without a lot of visual clue. These can be low top, they're hidden. And so embedded thunderstorms, even though they're typically not severe in nature, are actually a noteworthy candidate for one of the more dangerous types of thunderstorms that we discuss here. The line of thunderstorms, as you can see in the background, presents its own challenges. Say, for instance, here, you're trying to fly from, let's go with my background here, Dallas, Fort Worth, and you're trying to fly out here to Midland. One of these instances where, what do? Do you try and shoot the gap in a couple of these regions? Do you take basically double your flight time and come around the tail end of the system? And so this is going to be one of those instances in which there's a lot of thought process as to how you attack such a feature, but it is something that, again, you're going to want to avoid and cannot simply just go over a line of thunderstorms in this scenario. And finally, an area of thunderstorms, the MCC type setup per se, a large area of thunderstorms. And so we're not necessarily going to focus in on isolated thunderstorms, features that maybe air mass type thunderstorms over the southeastern United States. But the embedded thunderstorm's dangerous, the isolated thunderstorm should be visible, and if we get enough isolated thunderstorms, a maritime tropical air mass type afternoon, all of a sudden we may have enough of an area to be able to issue some type of convective SIGMET. But as we see on this final slide, they're going to be small in nature. Little polygons that are here. We can see Wisconsin, Lake Michigan, Ohio, and Pennsylvania, West Virginia. And so it's not like with the AirMet that we're going to connect all of these features. We're going to put out small polygons to show where the thunderstorms actually are occurring. And so I highlight the one here over Oklahoma and Texas. You can see sometimes they're interesting, developing line of severe thunderstorms, 20 nautical miles wide, moving from 250 at 15, tops above flight level 45,000 feet, tornadoes, hail to 4 inches, wind gusts to 60 knots possible. Suffice it to say, this will get a lot of visibility amongst the aviation community and is one of the more important things that meteorologists produce. I'll end the semester on noting that Area 1 does use GGG as one of its coordinates. Thanks for listening. We'll see you in class.